Hello everyone. Thanks for following the etracer users group on Facebook. Today's topic, I'm going to show you how to add a gas test function to etracer by a hardware modification. And this project is inspired by a etracer user from Australia. His name is Anthony Graham. And he had problem testing a D3A tube on the etracer with a SBox 12. And so I asked him to send me the tubes so that he can try on my setup. And I found for those very high GN tubes, the long wire gives problem to etracer for it causes oscillation. So I was trying to fix this problem by adding some grid stop resistor close to the tube socket, and then I figured it might be a good idea to have the ability to change the resistance in the grid circuit and to provide so first it can be a grid stop resistor, and secondly it can also provide a test code gas test as can be found in the old tube tester like TV7. So then I came up with this document, so we are going to go through this document today, and I'll after modifying the document, I'll put it on our website. So first, if you're interested, you can follow the document to modify your etracer hardware. So gas test can be found in like I said, it can be found in the tube testers, like fancy tube tester like a TV7. So the theory or the assumption for the gas test is if a tube is gassy, there exists a non-zero grid current due to leakage paths between electrodes under negative grid bias. So theoretically, under negative bias, the grid resistance, the resistance you look into the grid should be very, very high, like several mega ohms. But if there is a leakage, you'll see grid current. And the assumption is the more the amount of gas inside the device under test, the higher the grid current. But according to a book written by I think Robert Tomer, in the reference section, it's the name of the book is Getting the Most Out of Vacuum Tubes by Robert B. Tomer, written in 1960s. The grid current, the gas current, the grid current caused by gas is not the only source of the grid current. Actually, there are four major components of a grid current. So this figure 1 is extracted from this book. So here we can see the x-axis is the negative grid voltage. So here we can see there are four sources of grid current. The first one is the initial velocity. This one, I believe, is caused when we heat up the cathode by the heater. The electron emitted from the cathode will hit the grid. So at a very low grid negative bias, we'll see a lot of this grid current caused by the initial velocity, by the electrons. So the y-axis is the amount of grid current. So there's be careful of the sign. This is a negative sign, this is positive sign. So basically, if the current is in this region, we'll see the negative, the grid will go more negative. And if the current is in this direction, we'll see the grid, the voltage on the grid tends to be higher than the bias voltage supplied to the grid. The second source is a gas component. the third source is a grid emission. Grid emission can be caused by the pollution to the grid. So when the grid electron is heat up, it will release the electron and cause this grid current. And the last one is a leakage current. I think this is probably something due to a leakage path between electrodes. So if we carefully look at this graph, we know that the direction of the grid current is not necessarily in one direction only, because if you look at this region that where the negative bias is very close to zero, the current caused by initial velocity is very high. So if we sum all these curves, we can see the current will go let's say in the upper direction. But if we measure the current here, then we probably see the current go in the negative direction. So if we want to measure the grid leakage, the grid current, we probably need to make sure that our bias is negative enough to avoid this huge amount of the initial of grid current caused by the initial velocity. But even we sum the grid current here, and even we measure the grid current here, although they are all in one direction, but this is not saying that the grid current caused by gas is the only source. This is we should keep in mind. But even though we know the gas current is not the only the source of the grid current, and by measuring grid current not necessarily indicate the how gassy the tube is, it's still might be good to have to add the gas test function to etracer, because with the capability of etracer, it can actually do much more things than a TV7. So by inserting a different resistance to the grid circuit of the etracer, you can reveal much more like things related to the device under test. Okay, so firstly, so here we want to check how gas test is done in a TV7. So figure 2 is a circuit excerpted from the TV7 service menu. So here is a simplified gas test circuit in TV7. This is the device under test, and the plate is supplied by the supply voltage by the power supply in TV7. The cassette. So this is the cassette. And this is a grid circuit. There is a bias. There is a grid bias voltage supplied by TV7, and here is a switch. So this is a push button switch. When the switch is closed, these two wires are shorted. When the switch is open, okay, so let me put it this way. So when the switch is closed, the bias voltage will be shorted to the grid because this switch is shorted. So when this switch is open, the bias voltage will flow through a resistor with a resistance of 180K before it hit the device under test. So the way the gas test work in TV7 is, first you measure the plate current with the switch shorted. So other words, the bias voltage will appear on the grid circuit. And secondly, when you open this switch, so and measure the plate current again. So this time the bias voltage will be connected to the grid of the device under test with a resistor in series. So if there is a grid current, the grid current will flow through this resistor. So the voltage here won't equals to the voltage here. So you can in TV7 menu it assumes that the direction of the grid current is always in one direction. It's in this region. So if you look at the sign here, this is positive, this is negative. So this is a negative power supply, and it assumes that with the grid current, the voltage drop here will cause the voltage on the grid at a higher potential than this bias voltage. So as a result, you will see an increase on the plate current because the voltage is higher on the grid. So the difference in these two plate current give you a indication of how gassy the tube is. So and you can put that into a percentage. And I don't know the percentage, the criteria for used by TV7, but you can put like 1% or 2% difference of the bulky plate current, that kind of criteria. Okay, so now we understand how TV7 performs the gas test. We can check how we can modify the etracer circuit to supply a similar test. So here in figure 3, this is the grid bias circuit in etracer. Okay, so during the C42 is the 47 microfarad capacitor. So during the charge phase, C42 is charged to the target voltage, negative voltage, and during a measuring pulse, this control signal will turn the solid state relay U20 on, so it short the path here. So the voltage, negative voltage on C42 will appear at the output of the at the neg V output. Here is a fuse with a very low resistance, and so during the measurement phase, C42 is more like a battery. Oh. Okay. C42 is like a battery. Let me check. Hold on. Okay. So so the output impedance is very low. It's basically the ESR, the equivalent series resistance of C42, which is in the order of I don't know, a couple ohms. Actually, it's probably less than 1 ohm. So it's very low. So how do we modify the hardware to support gas tests? Actually, what we want is we just put the resistor here before we connect to the device under test, just like TV7. So if we make this resistance selectable, we can actually supply different values of series resistance to the device under test. We must we have to know that because this output impedance is very low. So if we remember, etracer can test a twin triode simultaneously because etracer has two high voltage supply. So what we do is we just connect this guy to the grid of both sections inside the twin triode. So this is okay because the ESR, the output resistance is really low. So the voltage appear on both sections should looks similar. But if we have a very high resistance in the grid bias path, we will need to separate the resistor to each section. We will need to use different separate resistor to each section. Otherwise, the grid current will affect the bias mutually. Okay. So here the modification methods I used a lever switch. It's a DP/DT double position dual position dual throw switch, and it's a on type. So with this configuration, we can support 3 different type of resistance. So they are short, 1 k ohm resistance and 100 k ohm resistance. So this 1 k ohm resistance and can also be used as a grid stop resistance. So if you are testing some really high GN tubes, you might want to put the 1 k ohm resistor like the mini amplifier does to prevent the circuit from oscillating. So besides using the lever switch, you can probably use potential meter or multi-position rotary switch to support even more values of resistance. But we have to do this in caution. So below we have 4 notes we need to talk about. So the note 1 is the location of the resistance selector should be placed very close to the tube sockets as possible. Give me a second. So the USB cable is very unstable here. Every time I touch it, it breaks the etracer connection. So the note 2, the 1 k ohm resistor can act as a grid stopper, like just said, to eliminate the oscillations from for some very high GN tubes. So far, I don't see any problem with any tubes, but this might might be nice to have if you decide to add this gas test function to your etracer. Note 3, the negative V can be very high. In etracer, it can be as high, actually as low as 200 volt. The difference between negative V and the ground will be 200 volt. So the voltage rating for the pulse. So for example, you decide to use a potential meter over like a rotary switch. You have to check the voltage rating of this part. So note 4 is like what I explained. If we need to separate here on the etracer chassis, we have 2 banana jacks for the negative V. In the original design, these 2 are shorted, but if we are going to put resistance in the grid circuit, we need to separate these 2. So we need to disconnect these 2 banana jacks and treat them separately. Otherwise, the grid current of one section will interfere the grid bias in the other section in the twin triode. Okay, so that's the reason why I use the DP/DT, the double position double throw switch instead of the single position double throw switch. So in figure 4 is the connection we want to do the etracer. So this big switch is a double DP/DT switch, and it actually has 3 positions. It's a on-off-on type, which means besides the 2 on state, it has an off state. So let's give them the on these 3 states number, position 1, position 2, and position 3. So here, this is a negative output from the etracer PCB, and let's assume the switch is in position 1. So which means pin 1 and pin 2 is shorted, and pin 4 and pin 5 is shorted. In this position, the negative V is shorted through P1 to pin 2 to the negative output 1. This is one of the banana jack, and this is the other banana jack for negative V, the yellow one. And for this path, the negative voltage will be shorted from pin 4 to pin 5 and all the way to the banana jack number 2. So in other words, this is the default position before the modifications. The negative V is directly appear on the banana jack. So if the switch is at position 2, which is the off position, then this switch is connected to nothing. So the negative voltage will be connected to negative output 1 through this 100k ohm resistor. And the same thing here, because the switch is disconnected from anything, so the negative voltage will go to the banana jack number 2 through this 100k resistor. Okay, I use 100k instead of 180k as in the TV set, because I don't have 180k in my toolbox, so I just pick 100k. So if you want to make the hardware the same as your TV7, you can use 180k ohms here. So if the switch is at the position 3, which means pin 1 and pin 3 is shorted, and the pin 4 and pin 6 is shorted, then for the upper branch, the negative voltage will be connected to the first banana jack through this 100k ohm resistor in parallel with this 1k ohm resistor. Because this guy is very high compared to the 1k resistor, so the equivalent resistance will be very close to 1k ohms. And the same thing here, because pin 4 and pin 6 are shorted, so basically these 2 resistors are connected in parallel, so there will be a almost 1k ohm resistor between this negative voltage output to the banana jack on the top plate. Okay, so with this modification, we at the 3 different positions, we can provide 3 different resistance between the negative voltage output of the PCB to the grid of the device under test. Okay, so here is a gas test procedure after the modification. So the test will be done manually, so it's like similar to TV7. So let me show you here. So this is the D3A, and the heater is turned on for a long period of time. So I got this D3A from Anthony Graham, as I said in the at the beginning of this video clip. So firstly, we put the position at the short position, and we run a quick test. Okay, then we can record the measured plate current. It's 19.3 milliamp. Now we can put the switch at the 100K position. So this will put the 100 ohms resistance between the power supply to the grid of the device under test. Then we run the quick test again. Okay, so we see the plate current goes to, now is 19.55. So it's about 0.2 milliamp increase, like described in the TV7 menu. So this amount of increase is reflect how gassy the tube is according to the TV7 menu. So you can decide, you can probably put a criteria, say if it's within 1% of the target of the reference menu, it should be okay, something like that. Okay, so basically this is a gas test done manually. But with etracer actually you can learn more things with a full scan. So maybe let's try this very high GN tube. So we put the switch at the 0 ohm position, and we can run a full scan. Okay, so this D3A is a pentode and is triode connected. So here we can see a very interesting behavior. I don't think it's oscillation, but if we look at the screen current represented by the curves in green, you'll see in this region the green current looks weird. Okay, we don't need to go to run a full scan here. We can probably stop here. So now if we put the grid resistance to 1K and run the test again, okay, so first thing we observe is the screen current is much smoother than the previous one. The second thing we observe is the current at 0 bias point is lower than the current measured when the grid is shorted to the negative voltage supply. So this is caused by the initial velocity as described in the book, in Thomas' book. So if we do a gas test here, close to the 0 volt, instead of a plate current increase, we actually see a decrease in the plate current. So now let's put the switch at 100K. Here, this is the position we do a gas test and run the full scan again. Okay, we can afford. So this one again, this one is the plate current measured at 0 volt, 0 grid bias, but with 100K in the grid bias supply path. So this means the grid current is really causing a problem, and it makes the grid more negative. So we see the measured plate current is much lower, and this one even at minus 0.5 grid. Negative supply with this 100K ohm resistor, we still see the plate current decreased. So in this bias region, the initial velocity is very strong, and so the major plate current is not higher; it's actually lower. So when we do a gas test, we need to pick a bias point far away from this region. So maybe instead of doing perform the gas test at minus 0.5 volt, we need to do that at minus 2 volt or minus 1.5 volt, for example. So you can see, as supply voltage goes more negative, the curves are more or less overlapped, which means this tube under test is not affected by the grid current much. Okay. So this is about today's topic. And if you do, with this resistance, you can play with the tubes, and I believe you'll find more interesting things with assorted tubes. Okay, that's it for today. I'll see you next time. Bye.